All right, so I'm going to work through an example of some kinds of problems that you'll see in homework 4. So hopefully this will be helpful as you try and look at the homework. Just use this as a kind of prompt for working through some of the questions. So again, I've got a working directory here. Familiar with that by now. I'm just going to read in a data set. It's just really pretty arbitrary. I'm just working through the kinds of examples. The data have nothing to do with the homework. I'm going to create a subset of the data just for fun here. And let's just look at a summary so you can see what's there. I've got a y variable, x1, 2, and an x4. And so that's what I've got going on. I'm going to make a 1 over x variable for one of these. So I'm just going to see how to create a new variable, make a transformation. So I'll say tr, that's the name of the data set that I've got. So tr, I'll say x4 I and b. So it's going to be inverse of x4. And what is that then? It's going to be tr x4, and then it's 1 over that. So just get that going there, and I've got that. Now, what I might do though here at some point is I want to look at the relationships amongst these variables just in a bivariate scatter plot. So, so I'm going to have that actually down below, but I can create that here. I'll just say, well, let me actually do this here first. Let me just get this out that I've got, and I'll just say pairs tr, and it creates these plots over here. Now, one thing to note then about these relationships is between y and x1, maybe it's hard to make much out. Same thing, x2 and y, same thing, x4 and y, x4 inverse and y, maybe not much to see, but you hopefully can see the direct relationship between x4 and x4 inverse, right? That's giving us this plot here. So I'm looking down at the bottom right-hand side. You can see what that inverse relationship looks like. Hopefully that's apparent to you. So looking at those plots can be helpful in some cases. Here, we don't have much going on between y and x1, x2, x4, at least not that it looks like. We want a histogram though of, let's just say y. So we'll just say histogram tr, and let's just look at y and run that. And we get this roughly bell-shaped looking plot in this case, right? So in this example, it has that basic shape. Obviously not perfect, but has something approximating it in this case. So, all right, log transformations. How do we make log transformations? And let's go ahead and get those into the data set. So let's just look at two variables we'll go with here. So I'm going to have tr, and I'll go ahead and call it lny. And what should that be? Let's just have it be log of try. And then let's make one also for x4, we'll say, and have that be log. Oops. Could have left it with low and it would give me an error message. In fact, let's just do that just for kicks here. Leave it like I had it and it'll give me an error message. So I have this going, and then gives me error message down here. Right, I hit the W key instead of the G key. So it should be log up here, and now that'll run. Okay, so again, anytime something doesn't run, just check out the error message. see what it's telling you. Try and use that as a guide for troubleshooting. I want to give you something there. Now I can go back and run this pairs again. Now I've got two more variables in there, and you'll see some additional relationships coming out from that. So let's just go ahead and run that. So now maybe it gets a little harder to see because there are more variables in there, but you can probably see now, hopefully, this. Oops. Grab this pen. You can see this relationship. Oh, let me just get this pen here. So we've got natural log of y and y, or you can see what it looks like going the other direction, right? Natural log of y to y, right? So you can see what this relationship looks like, right? So that's just getting a feel for the plots and how the relationships might work, how things might look. Okay. You can use this pairs, or you can just create individual plots. Your choice about some of that. All right, so you've got these log, or you've got these log transformations, these log variables. We're going to run a regression here. You've got some different options in this case, but let's go ahead and go with this idea here. Let's go with the log y and the log of x4 and data equals tr, and we'll just go with summary for m. Now, again, these data don't, taking logs doesn't necessarily mean a whole lot. What we've got going on, there's not much going on. I'm just running through an example. In other settings, right, why might we be taking the log? We might be doing that because we're trying to estimate an elasticity, a percent change in one variable. How might that relate to a percent change in the other variable? And in this context, not really very meaningful. We don't even know what the variables are. We're just running through things. And you can see here, R square is very small, right? This is not statistically significant. We just got whatever going on. But let's suppose we have these results, which we do here, and we just want to test a hypothesis. So this is a review of testing a hypothesis. In this case, the coefficient is 0.5. So this is a two-tailed test. How am I going to work through this in this case? Well, I want to find the test statistic, and there are a few different ways of going about that. But in this case, I could say that t equals, and you can go back and look at some previous examples, but you're going to take the parameter estimate. So that's this value here, the 0.04661, put that in there, minus the hypothesized value, so that's 0.5, it's this right here. And I divide that by the standard error. So I'm just going to copy that out down here. 0.23054. Now, let me just note for you here that you can get more precise values. So again, just as a review, we could look at something like this, say summary M, and I'm going to go with coefficients, and I'm in this table, and I'm going to want the second row, second column. So with this, I'm hoping to get the standard error out if I've typed it in correctly. Let's just look at that. And I have, and you'll notice that it gives me the 0.2305, but not 4. It says 371, right? So it's rounded up here. So if you want to get more precise values, which hopefully you do, you want to get them as precise as possible. But here I'm just taking a little maybe shortcut, as it were. But this is how you're going to get the t statistic. So run through that. I get a t value, and then I can come down here and let's just print it out and see what it was. Negative 1.9664. Okay. So now I want the p-value associated with that. In this case, it's a two-tailed test because it says the coefficient is 0.5. So how do I get this out for a two-tailed test? So I'm going to say p-val equals, for a two-tailed test, it's 2 times. And in this case, I've got a negative test statistic. So I'm just going to say pt instead of 1 minus pt if this were a, so again, is it a left-tailed test, a right-tailed test, a two-tailed test? Those are things to pay attention to. Go back to your things from the prerequisite course, your statistics class, business statistics, to check that out. But in this case, I've got a negative test statistics, two-tailed test, so I'm just going to go with 2 times pt. And what do I have in here? I have the test statistic value. So I didn't save that. So, oh yes, I did. So it's t, right? So I saved that up just on the line before, right? So that t. And then I need to enter the degrees of freedom. How many degrees of freedom are there? There are 83 in this example. Show you where the 83 is. It's this 83 right here, where that's coming from. So that goes in there. All right, so this is my p-value. Whoops, something's a little goofy with my mouse, but run that. And then we'll just ask what the p-value is down here. And it says it's 0.0525. Okay. All right, I've already run the pairs a couple of times, so hopefully that's familiar to you now, a way to get out the scatter plots. Something else I want to do is do this Box-Cox analysis. So I've got this mass library, I've already run it, but I'll just click on that again. And all that I'm going to do then is type in Box-Cox and the model, which I called M before, and just run this and see what this does. And I come over here and look at it. It looks a little unusual, a little, maybe call it funny, but typically you're going to be dealing with things that would be between -2 and 2. And in fact, that's the way that R is plotting this out as the default. But if I'm looking at this plot here, right, the 95th, it's 95% confidence interval for the parameter estimate. This lambda is what it's called. You can see lambda down here. It says that at the lower end, it's just a little less than 1, and it goes out here somewhere a lot bigger. I can't see that, so maybe I think it goes out to 3. So let's just check that. And how would I do that? I come back over onto the code line and I say lambda equals, it's going to be a sequence from, let's just start it out at something a little less than 1, let's say 0.8. I don't know how far it goes. Let's just say maybe it goes out to 3. And let's do it by 0.01. That's just the increment there. And see what this does. Oh, it's bigger than 3, right? Even at 3, it hasn't shown me the peak. So let's try 6. Let's just play around with it here. And see, I already know this isn't going to work either because I've already gone through this, but 6 isn't big enough. Oh, gee, maybe let's try 12. Gosh, what do we need to do here? You're just playing with it. And there it seemed to work, right? And now it looks like it's somewhere between 6 and 7. Or sorry, 6 and 8. So I want to maybe narrow that down a bit. So maybe I take this and say, oh, I think it's somewhere between 6 and 8. Let me see if I can find where that peak is, or the ideal lambda, and just run that. And yeah, it's close to 7, right? Now in practice, you're not going to see something that looks quite like this it's very unlikely, right? So go back to the lecture notes on this. This kind of scenario is a bit unusual. So don't get too worried about it. Just purpose here is that you're seeing, you type in the Box-Cox, you can look at the graph and figure that out. You can also use the power transform function. There are other options, but we'll go with that for now. All right, so now we've got a test for normality. So what this suggests is you would apply a transformation of raising, again, we had this log model. So you would raise the natural log of y, raise that to the 7th power is what this is saying to do if you're regressing it on the log of x4. So sounds a little strange, but that's what the interpretation or meaning there is. So I want to test for normality. I'm going to do a Shapiro-Wilk test. So a Shapiro test, that's what it says there. And I'm going to use the standardized residual. So R standard for my model, M, and see what this gives me. Run that out. And it gives me a low p-value or a small p-value. At least it's less than 0.05, right? 0.0003185. So that suggests that I'm going to reject the null hypothesis that the residuals are normally distributed. In fact, I can plot this out. Plot M. I'm going to have to go through this a few times because I didn't do the. Anyway, we'll just check this out. All right, so I down here hit enter. The next plot's the one that matters, right? So this is the QQ plot, and it just suggests that it's a little off from what would be normal, right? I'm going to hit this a couple more times just to get through this. There we go. All right, so I'm rejecting the hypothesis that the residuals are normally distributed or that the errors are normally distributed. And so that's where I am. Well, one thing that a transformation might do is it might help to get the residuals into a normal pattern or normal distribution. So let's just check what happens if we modify this regression. So I'm just going to copy paste up here. Copy. I'm just going to paste this down here. And I'm going to make a change. I want this to be model, I'm going to call it 7 because I'm going to apply a transformation that was suggested by the Box-Cox, right? So I'm going to raise this to the 7th power. So now the dependent variable is not the natural log of y, but it's the natural log of y raised to the 7th power. So hopefully that sounds a little weird to you because it is, but that's what the Box-Cox analysis suggested in this case, right? These variables are they're just made up. Right? So that's what has going on there. And let me just go ahead and run this model 7. Ta-da. And then do this Shapiro test again. So I'm just copy paste here, so I've got it right there. But now I want this instead of on the model before, I want this on model 7. So now if the transformation was helpful in this sense, you might think that it's going to transform these residuals so that they appear to be, it's not transforming the residuals. I'm getting new residuals from this new model, but these residuals might have a distribution that's more consistent with normality. So let's just check that here, run, and indeed I get a larger p-value here, one that suggests that they're more consistent with being normally distributed, the residuals that is. So in this example, I would not be rejecting the hypothesis that the errors are normally distributed. Okay, so there's just a walkthrough of some of the kinds of problems that you'll see. Of course, refer back to the lecture notes and videos and the quizzes for other examples and types of questions. But hopefully this is a good start for what you've got going on and will help you to just at least get started with and work through the homework. So good luck.